Okay, can I start?
Yes, please start.
Okay, I'll be talking about the universality, simple algebras, and configurations of points and lines. I hope the talk will be interesting, and let's start. My present research is rooted in the notion of universal simple algebra, which is a certain tensor category, which has the Vogel plane as a moduli space with special points corresponding to all simple algebras. Let me recall you that a Vogel plane is the quotient space of projective plane with projective coordinates alpha, beta, and gamma, which are called in this context as Vogel's parameters, by the symmetric group S3 acting by permutations of these very parameters. Here I present the so-called Vogel's table, which lists all the special points in the Vogel's plane corresponding to simple Lie algebras. Here I've chosen the parameterization with alpha equals to -2. And let me note that the projective nature of these parameters, like the opportunity to choose the parameterizations, corresponds to the fact that the invariant bilinear form on simple Lie algebra is unique up to a multiple. Here I present a quite famous picture. It is the distinguished lines in Vogel's plane. The main fact is that the special points which correspond to simple Lie algebras are in this Vogel's plane are situated very non-randomly. For example, as you see, the exceptional simple Lie algebras, for example, lie on one line, and so do the other algebras, such as orthogonal, unitary, and symplectic ones. On the right corner of the screen, I presented the equations of these famous lines. And now let me present the notion of universal formula. It is known that some numerical characteristics of simple Lie algebras can be expressed by analytical functions of only 3 Vogel's parameters by some formula. And this formula we call as the universal formula. As an example, I presented maybe the simplest universal formula, which represents the dimension of any of the simple Lie algebra. In fact, you input the corresponding coordinates in this simple and beautiful formula, and you get the corresponding dimension of the corresponding algebra. Since the initial work of Vogel, several universal formulae in the scope of the representation theory of simple Lie algebras have been derived. Particularly, I want to present a formula for the Cartan powers of arbitrary powers of the x2, so-called x2, and the joint representations, which appear in this presented decomposition of the anti-symmetric square of the joint representation. Recently, I with my supervisor have derived this following formula. As you see, in comparison with the previous one, the dimension, this formula looks far more complex. You can easily notice it. And then we propose a natural question, namely, can one find another more simple looking formula with the same outputs at the points from Vogel's table? Or generally, are the known universal formula unique? To solve this problem, we observed the following fact that all known universal formula share this structure of being ratios of products of the same number of linear factors of Vogel's parameters with integer coefficients. And now we are trying to find some new formula with this same structure and yielding the same outputs at the corresponding distinguished points. Evidently, if Q1 and Q2 are two universal formula with these particular qualities, we can see that their ratio is also shares the same structure and obviously is yielding 1 at the associated points. Then we write the general expression for such a Q with yet unknown coefficients n, I, xi, etc. And we impose Q to be equivalent to 1, not only on that particular points distinguished corresponding to simple Lie algebras, but on entire lines on which the points are lying. For the beginning, we choose 3 distinguished lines, the SL, SO, and exceptional, and make a change of a projective transformation such that these corresponding lines take the simplest form, namely alpha equals 0, beta equals 0, and gamma equals to 0. And solving the imposing QA being equivalent to 1 on these 3 lines simultaneously, we come up with this solution. We come up that Q must be of this form, and the parameters unknown must satisfy these following sets of equations for some permutations Si and Pi. I would like to note that the permutations must be chosen before solving these equations, and later I will speak about in more detail. Then we notice a very beautiful geometrical interpretation of this universal dimension formula. It is pretty straightforward, so let me explain. If you take the factors in a universal formula, the linear factors, it is easily noticeable that each of the factors is in one-to-one correspondence with some line in the Vogel projective plane. Indeed, if we take the line with the same coefficients and make it being equal to 0, we have a line which is in one-to-one correspondence with the factor of taken from the universal formula. This ultimately means that any universal dimension can be depicted into the projective plane. To illustrate this fact, I did a sketch of the simplest universal formula. Here you see it with the particularly chosen parameterization. And now let's turn to our functions Q. Obviously, for any Q, which is written for, say, K multipliers, we can sketch a picture, a unique picture consisting of 2 K lines plus L distinguished lines. And for simplicity, I colored the distinguished lines in black, those corresponding to the factors in the numerator, I color in red, and correspondingly the remaining factors, which are corresponding to the denominator, I color in green. And specifically, each of the black lines must contain K points at which a green and a red line intersect. This is to satisfy our requirement for Q to be equivalent to 1 on these distinguished lines. Indeed, if you take a black line, say alpha equals to 0, 1, all factors all factors in the numerator take the form. Like the factor with alpha disappears. And from the condition for Q being equivalent to 1 on a black line, it follows that for each of the factors of the numerator, there is a proportional 1 in the denominator. That is, this following equality holds. This in the geometrical language means that the corresponding lines pass through the same point, as you see in this little sketch I present here. So In fact, we have 4 K points at which precisely 3 lines meet, a black, a green, and a red. And if we require that each of the 2 K plus L lines contain precisely K points, we will be dealing with a well-known geometrical notion, a configuration of points of line and lines. And let me remind you of the definition of a configuration. It is a set of P points and L lines such that at every point precisely gamma of these lines meet, and every line contains precisely pi of these points. It is easily deducible that P gamma must be equal to L pi in order to have a geometrical configuration. Back to our problem, we came up that we're dealing with the following configuration presented here with KL points and 2K plus L lines. And now I started with imposing Q to be equivalent to 1 on 3 distinguished lines, and I came up that I'm dealing with a famous 9-3 configuration, which has been known since 4th century. It is a well-known and famous configuration. I presented in this slide. And then I went on with imposing Q being equivalent to 1, now on 4 distinguished lines. And then I will be dealing with the following configuration with 16 points and 12 lines. Some examples which are known in the scope of the theory of configurations I presented here. And now I present my main results. Taking a known configuration, it appears that I can deduce an algebraic universal formula. So the main fact is that this configuration contains the information about the permutations I was talking about before, the permutations which I must take to solve the equations I derived. So it turns out that if I have a known configuration of points of lines, I can deduce a universal formula which is totally algebraic. I did it with 3 black lines using the famous Pappus configuration and derived the following universal factor. It means that I derived a function Q, the desirable function, and notice that it has some free parameters in it. It corresponds to the fact that I can make some projective transformation with the configuration to the configuration itself, and it will remain a configuration after these changes of the free parameters present here. In case of 4 black lines, I took this following configuration, colored the lines so that it meets the requirement that at each point, three lines of different colors meet, as you see here. And tracking the patterns of cancellation in Q by just tracing the intersection of the points, I was explicitly dictated by the choice of the set of the following permutation, and I could manage to solve the following sets of equations with these inputs, and finally derived the following Q non-uniqueness factor, as I call it, with these following C, Y, and X free parameters, as you see. And it is interesting that I could take a picture, a totally geometrical thing, and correspond to it a totally different thing, like totally algebraically, and which corresponds to some simple Lie algebras, etc. Now let me say a few words about the main open problem. Recently, it has been discovered that all known universal dimension formula for simple Lie algebras, they yield reasonable outputs when considering them with permuted Vogel's parameters. Here are the publications in which this following fact has been derived. And in order to preserve this feature of a universal formula, when multiplying it by some q, we impose the letter to be equivalent to 1 on entire 12 lines in the Vogel's plane. The 12 lines are presented here and can be derived from one another with the permutations of the parameters. And from the geometrical point of view, this totally symmetric function would be corresponding to the configuration which has 144 points and 36 lines. Unfortunately, I couldn't be able to find this type of configuration, and so that the uniqueness factor, the desired Q, can be found either after constructing the configuration or by choosing another method. So ultimately, we set up a correspondence between two classical areas of mathematics, which are simple Lie algebras and geometrical configurations of points and lines, which is indeed, I think, very interesting. And thank you for your attention. If you have some questions, I'll be ready to answer them. Thank you.
Thank you very much for your talk. Please, some questions or comments? Okay. I have a question. This G module X2, is it always reducible for simple Lie algebras G?
Not always. It may be. It depends on the automorphism group of the thinking diagram.
Okay, and multiplicity of G in lambda to G is always 1, or
is always 1? Yes, it is. It is a universal decomposition up to the automorphism group of the thinking diagram for X2. I mean.
So by this reason, G is G module not contained in X2.
Yes.
And also, could you please show two slides over with this diagram number 4 here? Yes.
Here, this.
This appears also this D21 alpha. Is it what is it not?
Super supergroups. Yes.
Super.
Supergroups.
And it only one appears here, or you of course you didn't speak about.
No, it is the supergroups D21 lambda depending on lambda. They are parameterized by lambda and are lying on the one line you see here.
And other
you come up with a supergroup.
Sorry, and some other supergroups appear also here, or only?
I'm not sure, but I think yes. You can depict them on the Vogel plane.
Okay. Thank you very much.
And thank you for your questions.
Maybe some more questions or comments? Okay, no more questions.
Okay, thank you very much for your attention and this opportunity.